Well, and here we are again, now for the last part about half transform. Promised after that you won't see it anymore in the lectures at least, which deals with a different topic. So far we had like one aspect or one video dealing with different representations of the linear half space. The previous video was about detecting like nonlinearities and how the nonlinear half spaces can look like. The third and last aspect is, since we are searching actively in half space for these regions of interest, for those dense regions where the functions intersect, how can we achieve that? With the title, Let Me Find That For You, about the search strategies in half space. So a bit of an history. The very first half transform techniques approached it the following way. They said, okay, if we have, for instance, like the polar form with angle and distance, we impose a grid with a fixed resolution, and then we start counting. Like this grid cell has one function intersecting, that one here two intersecting, and so on and so forth. And then through a majority vote, so like saying this one here is like one with most number of cells intersecting, number 6, this is what we are choosing. The problem is that depending how fine you select that grid, you will have to compute or check a lot of grid cells. So if we would make these cells much finer, we would have much more cells to check, and this is expensive. What can also be done, what can also be critical, is if you go high dimensional, then you have like exponential more cells. Here you have like quadratic, so if you have like 1, 2, 3, 4, 5, 6, so you have like 6 or 7 or 6 square at least. And then in 3 dimensions, you have like 6 to the power of 3, 4 dimensions, 6 to the power of 4, and so on and so forth. So that's not feasible at all. Then we have this approach of the half transform in half transform search for as used in cache. Here you see again how it works. So it has an iterative bisecting approach. It starts first splitting among one predefined axis and then looks left and right, where are the most ones. And in a heap or in a priority queue fashion, it starts getting finer and finer and finer. The good part is it prunes away those large areas which are not interesting. So this is a really strong point of this method. And you get extremely quick, if you have idealized data sets, and this is something we will get to it, you get quickly to these green colored regions of interest. So what are the strengths and weaknesses of these two mentioned methods? The accumulator, it's plain simple. You just stupidly put a grid on it and say, start counting. However, the weaknesses, it generates many candidates with increasing grid resolution. It generates exponentially more candidate cells with increasing dimensionality. And you have, of course, a fixed grid resolution. So you cannot say, oh, hold on a second, I want to get finer on that cell. No, you have first to do it in one iteration and then later on refine the others. Then we have this iterative bisection approach, as we call it, from the cache algorithm. It inherits the efficiency from a depth-first search. It prunes early the regions away which are not dense enough, as you've seen in the previous figure. However, it can deteriorate, and this is one of the huge weaknesses, it can deteriorate to exponential runtime, especially when data is noisy. What does it mean? Let us go back here. Here you have like an idealized data set, where like you have 2 clusters actually where the objects are perfectly on one line and perfectly on the other line. Now suppose you have a lot of noise, then you would have here at these empty areas a lot of functions, and this would mean you would have this refinement much more frequent. You would have it here, you would have it there, you would have it here, even if the objects intersect and here. So in case of noisy data, which is not unusual in real world settings, consider a sensor and you have like some noise created by the environment. Then you get into trouble, because then you have many more of these cells to get finer and finer, and then it's like a binary tree where you go through each of the paths down and back and down and back. So you actually traverse the entire tree, which is of course of exponential nature. So you have like 2, 4, 16, 32, 64, and so on and so forth. So this is the bad part. The cache algorithm can deteriorate with this iterative bisection approach on extremely noisy data. So which other methods can you think of? And dear audience, I address to you this question. if you can think of any of these other strategies beyond these mentioned here, these 4 that we're dealing, do not hesitate to contact me. Let us go through. I'm excited because also in Munich when I was there, I discovered how students got really great ideas or brilliant ideas. Some of them did not work. Nevertheless, it was great pleasure or fun to go through it with them, to discover it, to see how the things work or do not work, what the limitations are. So if you have free time and are passionate or interested in this, I strongly encourage you, go for it. Now, these are the first 2 approaches that proposed, like the accumulator-based and the iterative bisection-based approach for extremely noisy data, as you see here. So this is a highly noisy data, and you see a lot of functions intersecting. We need a different strategy, what you see actually here in the first spots, how it seems to work. And there's another approach which may kind of be confusing to you. This is indeed a half space, but more on that later on that slide. So let's get to this picture here. What is happening here actually? Well, this is an approach that we developed like, I think 3 years ago with the assistant of a bachelor student. So it was a great time working together with that student. Also the citation up there, check it out and if you wish. So what is the idea? One idea is that we introduce a pre-processing step. We say, instead of taking all of these objects and look at their object functions in half space, we do something much more simple. We first perform a clustering algorithm. In this case, we use the mean shift. It's a mode seeking, so the objects keep shifting from all possible directions. If they are within a specific bandwidth, the bandwidth is something like an epsilon range. And then the objects, the black dots, they keep moving, and then they collide into one mode. It's like the center of mass, so to speak. This is the red dot. And the same for other objects here, and the objects that we have here, and the objects that we have here and here. After that, we convert these obtained modes, these red dots, from the mean shift to parameter space functions. So what we do then, we say, okay, for all of these red dots, create please the representation as object functions, these sinusoidal functions in half space. Then start rasterizing them. So try to quantize them into small cubes. And this is what you see here. So you have like this one red function split it into many red, green pieces. Then count the number of intersecting rasters. So here we have like an area where many of these greenish things start intersecting. And here also you have several, and here you have several. And then having those one which are most intersecting or k most intersecting, we determine like the lines and assign the objects to their respective lines. And as you see, we have here this green line, we have here this red line, we have here this yellow line, and we have here this blue part, this blue line. And what you discover here, unlike the original cache algorithm, it can happen that you have like overlapping clusters and where it says, again, first come, first serve, like cache, but it has also some sort of locality. So these blue objects are considered as their own line because we have like here those, for instance, from this area that are considered like belonging to one mode. So it is one way to dramatically reduce the computation because instead of looking at all of these dark lines, we only consider these red lines and we only consider from these red lines counting how many overlaps we have or intersections of these rectangles we have. So this is a quite simple approach to reduce the computational time on noisy data sets. So basically, this mean shift approach is kind of like a denoising step of saying, okay, you know what? I am willed to sacrifice the accuracy, because here obviously we sacrifice some accuracy and here as well, to get however much faster the results. So this approach C has as a novelty applying first mean shift, taking those modes that are the prototypes or representatives of the mean shift clustering, rasterize them, so make a lot of squares or boxes around them, and then count the overlapping boxes, and that's it. And if min points, so if we say at minimum that many squares or boxes are overlapping, then it is considered as one cluster, and we start assigning those objects to that particular line. So far about this one approach. And in experiments, we also see in the paper that if we have like 80%, 90%, so really extreme cases, it helps indeed of being faster than a classic cache implementation. However, it remains an issue that we have to check for intersections of functions. And this is kind of like annoying, because you always have to think in terms of how can I detect functions intersecting in this half space? But is there a different way? And the answer is yes. So the classic approach, as you know, in half space, objects become object functions. You're looking for intersections. Now, a different approach, also done together with a bachelor student and also published with that person together. It was a great experience. We take a different approach. We say, we have here, for instance, three functions, three objects. Let's compute in a two-dimensional space. We need two objects spanning a line. So let's take P1 and P2 spanning a line and compute for this the slope and intercept. This would be here, for instance. Then for P2, P3, let's compute a line, and this would be like this one here actually. And for P1 and P3, let's compute the line or its slope and intercept, and that would be this one here, the green one. So we keep sampling and computing all D tuples, so D for number of dimensions. If you have a two-dimensional data set, you're looking for all tuples of 2. In a three-dimensional data set, you're looking for tuples of 3. You recognize this is, however, getting exponential, because the more dimensions, the more tuples possibilities emerge. But this is how this fourth approach D works. And what happens, you get a lot of objects here. So you get here in half space, no longer object functions, but you get plain objects, plain vectors. It's a vector with the coordinates of a slope and intercept, slope, intercept, slope, intercept. And this is what we also got here for two-dimensional data set. If we take like all pairwise objects here, we get this one here. And then what you can do is quite exciting. In this half space, which is containing only objects of the, in this case, of the normal vector representation, as you've heard before, you get only vectors. You can start applying algorithms from clustering that you know beforehand from the KDD lecture, for instance. You can start using k-means here, you can start using dbScan here, you can start using mean shift here. And here I think it was like a mean shift based algorithm. And what we get, so these three crosses that you see, these dense spots that have been detected by an arbitrarily chosen algorithm, yield you then this particular line and this particular line and this particular line. So even in such a huge, massive, noisy data set, it detects you formidably these three lines. And this paper with the name of a Galaxy of Correlations, a short paper at the EDBT conference, was a different approach, making a cut of saying we are no longer scanning for functions intersecting in half space, but we try to sample it or to generate vectors. Each vector or each dot represents like one line here, and then start clustering. Of course, as you see here, it scales terribly with the number of objects. So if you have 1 million objects, you need 1 million over 2 or binomial 2 combinations. And it even gets worse. So in 3 dimensions, it's 1 million binomial 3, 4 dimensions, 1 million binomial 4, and so on. What you wish to do here is to perform sampling. And here, question to you as the audience. Do you know of any smart sampling strategies? How would you start sample? Would you sample uniformly? Would you use some Gibbs sampling? Is there any specific idea where you think, this would be a smart way of sampling here these objects? So for instance, excuse me, you do not wish to sample these objects here or these objects. They are kind of like, I mean, of course, you do not know beforehand, but so if you have any ideas about how to perform a smart sampling in this case, contact me and let's have a Zoom meeting and a nice talk together about that. And if you're looking for a master thesis. And yeah, this was it, the last part about the Huff transform. What do we have so far to sum up? We had different representations of linear half space. We had detecting nonlinearities, nonlinear functions, and how their half space looks like as the example of the hyperparaboloid or parabolic and the periodic. And we have here different search strategies for regions of interest in half space. This is it, and see you in the next video.